Okay, hi DiffyQs. So this is the lesson for today, Thursday, for my all boys class. And what we're looking at today are non-homogeneous differential equations and another method for solving them. And I should say, as I look at the calendar here, I think we're going to transition pretty abruptly. You know, we've kind of spent enough time looking at just solving DiffyQs, different methodologies, and then I'm going to skip to, something to land on some interesting abstract ideas like the Laplace transform. Okay, so I think this is going to probably be the last of these how to solve DiffyQ lessons. Okay, so we're talking about non-homogeneous differential equations. We're going to stick with constant coefficients, and I'm going to do a second order focus for us on these differential equations. Remember, these survey classes here. It's about just making sure I give you a pretty good taste of the course, but obviously we're skipping around, so I'm kind of picking and choosing as we go. All right, so a non-homogeneous differential equation, I just call them NHDEs for short, with constant coefficients has this distinctive feature, which is that it's not set equal to the function of x that is the constant 0, but it's set at equal to a function g of x. And probably the most important comment in this screencast is this, which is the general solution to an NHDE is going to always be a sum of the general solution to the associated homogeneous differential equation. And then here is the kicker, plus a particular solution to the non-homogeneous differential equation. And we're going to do a very simple, very, very straightforward proof of this fact. And then we're going to talk about an example. Okay. So this statement here is probably the most important. And seeing why it works is very simple. So here's the proof, if you follow me. So if you look at the blue here, whenever we start with a proof or whenever we do a proof, we have a givens and then we draw the conclusions from there. So what I'm saying is we're given here a second order DiffyQ, constant coefficients, non-homogeneous, okay? I'm making the assumption that g of x is not equal to 0. And the given information here is that we know that there is some function h of x that's a solution to the associated homogeneous differential equation, okay? And you know that there's a particular function j of x that's a solution to the non-homogeneous counterpart, all right? So those are my givens. And the question is, how do we show that therefore the general solution is going to be a sum of h plus j? Because that's what this statement up here says. Okay, well, if these two statements are true here, right, then it must be the case that if I input function h into the homogeneous for y, and input function j into the non-homogeneous for y, right, it should satisfy those DiffyQs, which is by very definition, what it means to be a solution to a DiffyQ. And if these two equations are true, we're going to revisit a really interesting idea from back in the day. If you have two equations, like two truths, there are a number of things you can do with them, right? You can add two equations, and that's what you did way back in the day of Algebra 1 or Math 1 when you solved a system, right? So I'm going to just simply add these two equations, and when you add those two equations, you get this, right? This equation right here. And that clearly shows you that the sum of the functions a plus h plus j does in fact represent a solution to the non-homogeneous differential equation, okay? And it is a general solution to the non-homogeneous differential equation. So here's an example here that I worked out. And again, for you all, I had done this lesson with your other class just because you guys are just one class day off. So here is the non-homogeneous DiffyQ, and solving the associated homogeneous, straightforward, nothing new here. This is all old news, okay? Then the task begins trying to find, okay, we're going to try and find y particular. I just call it y sub p, okay? Finding the y particular of the associated NHDE. And here is where we need to kind of think about it. And we're really making an educated, I hate to use the word guess, but we're making an educated, I guess for lack of a better word, but we're not like shooting in the dark as guesses go. Okay. I want you to think about something. And this is kind of the part of this class it's hard to do when it's just one way like this, and it's interesting because having done this live with your other class, it feels very different doing this exercise this way. I want you to think about it. There is a function, or what kind of function, right? What kind of function where if I took the function's derivative, if I took that function's second derivative and added it perhaps to a multiple of its first derivative, and then added it to a multiple of itself, what kind of function would potentially land me at 2 sine x? And I'm going to share with you, yesterday, Nicole had said, oh, it's like maybe maybe that function looks something like this. It's like some constant times sine x, right? So she was thinking like some constant times sine x, if I take itself and add it to its first derivative, which is cos x, and then add it to a multiple of its second derivative, which is negative sine x, somehow I can land at 2 sine x. And then Arusha had said, yeah, but you have that like cos x still lingering there, right? And then I think Nancy said, well, maybe that function is like some multiple times cosine x, right? But the same problem happens. Like, well, if this function is some multiple times cos x, right? Y is just that multiple times cos x. 2 times negative sine x, for example. There's my sine x, but then the second derivative of cos x lands me back at negative sine x. And this is where, at this point, I think it was either Jacob or Jason, I can't remember. They said, well, maybe y particular has the form of like some multiple of sine x plus some multiple of cosine x. And that is exactly right. So when we think about it, when you're thinking about this, it's let me just write this down first so I'm not multitasking. Okay, so when we were thinking about it and talking out loud about this possibility, we were wondering, what is the most inclusive form that the y particular could take that would allow, now listen to the sentence, that would allow for a linear combination of iterative derivatives to equal, at the end of the day, 2 sine x. And the most inclusive version of y particular is this, right? Because we have to allow for the possibility that y particular's function and its first and second derivative interact in a way that, all the cosines cancel out, if you will, and we're left with 2 sine x, okay? So while it is a guess in a fashion, it is very much educated and informed by our knowledge of the relationship between functions and their iterative derivatives. So now that we've made kind of a guess, we're going to figure out, well, what are the actual multiples of a and b? Like, what are these actual values here? Because if I can find those values, that will make this differential equation true, thereby satisfying the Diffie-Q, I have now found a particular solution. And the way we go about doing that, everyone, is we merely substitute. So if y particular is a sine x, then the derivative of y particular is going to be a cos x minus b sine x. And the second derivative of this y particular is going to be negative a sine x minus b cos x. And all we do at this point is we're going to substitute these back into the Diffie-Q and solve for a and b. I'm going to meet you there when I put it all in there. Arusha said at this point that it reminded her a little bit of partial fractions, right? And I see her point. I mean, not only is it the a and b that are used, but you're doing, you're solving for these coefficients, if you will. And I see her point there. Okay, so I've substituted into the left side of the Diffie-Q, and what I want this to equal is 2 sine x. Now, you'll notice that when I take a look at this left-hand side, I have certain cancellations. Negative b's cos x cancels out, positive b cos x cancels out, negative a sine x cancels out, positive a sine x cancels out, okay? And I'm left with 2a cos x minus 2b sine x has to equal 2 sine x. Now, from here, it's readily apparent if the left-hand side must equal the right-hand side, a must equal 0, and we found that b needs to equal -1. Okay? And what that does for us is we now know that my y particular equals 0 times sine x negative cosine x. Okay? Now, let's not lose sight of the fact that at the end of the day, right, we had to solve for the general solution to this NHDE, and my y sub general, right? I wrote y sub general here. That's the general solution to the homogeneous differential equation. So I'm going to say at the end of the day, my final solution, right, is a sum of these two things. It's y equals c1 e to the negative x plus c2 x e to the negative x minus cosine x. And here is your solution, your general solution to the non-homogeneous differential equation. Okay? At this point, Nicole asked, what happens if this g of x here is more complicated? And the first one she asked about was, let me erase this, hold on. Let me erase. Hold on, let me erase it. Whoa. Okay, there we go. She said, what if that right-hand side is not something like, cosine x or sine x? And she actually said, what if that right-hand side is a polynomial? And notice what I did here for this second example. I have the exact same left-hand side. All I've changed here is this g of x. So think about it. I want you to think about it. So now we're looking at thinking about the most inclusive form that the particular solution can take, okay? That would allow for itself and its iterative derivatives to be added up, linearly combined, right? Added up as multiples, right? That could be added up, that would yield 4x cubed plus x. You want to think of the most inclusive presentation that y sub p could take. Okay, and I don't think it's going to take you too long to get there, but the most inclusive presentation of y sub p would be a generic cubic, right? Ax cubed plus bx squared plus cx plus d, right? That's the most inclusive version for the y particular, like the family of cubic functions, okay? And again, you'd repeat the process by substitution. I think there was another example. There's one I think that I thought of that was quite juicy. What if you have this? I'll just keep the left-hand side, because left-hand side, that's really not, that doesn't cause us any great duress. Okay, take a look at this one, right? Again, look at g of x here. What do you think is the most inclusive presentation of the family of particular solutions here? I'll let you just think about it for a second. And I know this is just not nearly the same as, having us just kind of drop ideas, because the conversational piece of this lesson is really kind of indelible. Well, let's see. The y particular is going to be a some constant multiple of e to the 6x, okay? But then we have to account for sine of 7x. So it could be plus some constant multiple of sine of 7x plus some multiple of cos of 7x, okay? And then again, you repeat the process. This begs the obvious question. The obvious question this begs is kind of an extension of Nicole's, which is, what happens if g of x is a function that we can't, that not only that we are unable to think about a particular solution in that moment, but what happens if g of x is actually a function whose y particular is literally unknown. Like, we don't know. And therein lies, the limitation of this method of solving a Diffie-Q, right? So this is not an all-inclusive method for solving all kinds of NHDEs with constant coefficients. So this is limited. Okay. Now, you probably want to know the name for this. Okay, so the name of this method is called the method of undetermined coefficients. That's what this method is called. Okay, it's solving NHDEs by, I can go back here and even write it down. Oh, I did. Yeah, it's solving NHDEs by, it's called the method of undetermined coefficients. Okay, and I think it's the obvious nomenclature there. All right, boys, have a great day. And I think I see you live tomorrow, Friday, and I look forward to that, especially because I missed you earlier in the week here. So I'm feeling a little bit of withdrawal. All right, have a wonderful day. Goodbye.